Hello ladies and gentlemen, in this video we are going to be looking at different types of solutions. So the first type of solution we're going to be looking at are called electrolytes. Now I'm sure you've heard this word before, like if you've ever purchased a Gatorade or a Prime or a Powerade, they're going to be advertising that they have electrolytes. So a lot of athletes will be drinking electrolytes after they have, had a really hard practice or a game where they sweat a lot, or if you've been sick and dehydrated, you may be drinking something like that to help you get rehydrated or balance back your electrolytes. So an electrolyte is a compound that conducts an electrical current when dissolved in water. With a strong electrolyte, all of the solute breaks apart into ions. So that means it 100% disassociates or separates. The movement of the ions creates the electric current. So in this example here, this would be representing my ionic compound. So when it breaks apart, it's going to separate into its ions. Now we can have an electrolyte that doesn't completely separate. So it may only partially separate, like in this picture here. So if it partially separates, we call that a weak electrolyte. Okay, it still separates, so we will still have some ions in that solution, but not all of them do. Now, in a strong electrolyte, that's where every single ion will break apart from that ionic compound. So if we think about sodium chloride, like table salt, all of it will separate. So that would be an example of 100% disassociation. Now, what are electrolytes in terms of your body and what are the importance of them? They serve many important functions. So we can see that they balance fluids in your body, they maintain your blood's proper pH, and they also carry electrical signals from nerves to muscles. So some of these electrolytes are sodium, chlorine, magnesium, calcium, and potassium. And you can see that this is where you would actually get those ions from. So I have table salt, I have a tomato, our leafy vegetables, milk, or any other dairy, and then a banana. So some real life application is if you do not have proper electrolyte balance, you can actually develop heart arrhythmias. So potassium, magnesium, and calcium, those are all really important for your heart. Also, the sodium-potassium pump, which you may have learned about in biology class, this regulates your muscles and your nerves. So it helps with muscle contraction. And if you do not have the right balance there, you may develop some muscle weakness, some spasms, or some cramping. So that's why a lot of times after like a long marathon, you'll see that a lot of athletes will eat bananas because they're trying to get their electrolytes back in balance. All right, so how do we show if something's a strong, weak, or a non-electrolyte? So there is a test we can do with our light bulbs. So I have done this in class before where we've had a solution, an aqueous solution, and we put our light bulb in there to see if it will turn bright, if it turns, maybe like a little bit bright, or if it just doesn't turn on at all. So that's going to indicate to us how many electrolytes or how many ions we have in our solution. So sodium chloride, that completely separates into Na+1 and Cl-1 ions. So because it completely disassociates, we have 100% disassociation. So our negative ion is going to go to the positive electrode, and then our positive ion is going to go to the negative electrode. And that's going to allow our light bulb to turn really bright, okay? So that is where we would have a strong electrolyte. Now, a weak electrolyte is like mercury to chloride. So here we have our molecular picture. So I can see I have a +2 ion, and it is bonded with a -1 ion, which is chlorine. Okay, so that's why we needed 2 green circles here, because those are our chloride ions. We needed 2 of those for every 1 of my gray positive 2s. So looking at this picture, it may not completely separate out. So like we can see that we still have this ionic compound here, but some of it came off. So because it partially disassociates, we still get a signal. It's just not as bright as our strong electrolyte. Okay? And then we can have something like glucose or sugar that it dissolves, but it does not separate into ions because it's a covalent compound. So notice that we have carbon, hydrogen, and oxygen. There's no metal in that compound. So if it's a covalent compound, it may be able to dissolve if it's polar, but because there's not a positive and negative ion in that solution, we are not going to have a current, because in order to have a current, we need to have ions. Now, we can also talk about solutions in terms of their degree of saturation. So we can make solutions from a solid. So we can dissolve sugar into water. We can dissolve any ionic compound into water. So we either have a solution that's unsaturated, meaning the dissolved solute is below the saturated point. That means we can still dissolve more solid. Or we can have a saturated solution. That means the dissolved solute is at the saturation point. So if I were to put any more sugar in, it's just going to settle at the bottom. And then we can have a supersaturated solution, which is where we have dissolved solute is above the saturation point. So anything extra is just going to sit at the bottom. So when we're talking about this saturated solution, I always like to use a glass of lemonade. So if you've ever made a glass of lemonade and you're like, this is kind of diluted down, it's not very sweet, that would be an unsaturated solution. The saturated glass of lemonade, that's your perfect glass of lemonade. It's not too sweet, not too watered down. And then a supersaturated solution, that's where you have way too much sugar in, and where if you're drinking it through a straw, you can actually suck up some of that sugar. So that would be a supersaturated solution. Now, we can also make solutions with gases. So that's going to be like soda. If you've ever had a carbonated beverage, you can shake it up and you see it fizzes. That is the carbon dioxide that's dissolved into the water. So it says a bottle of soda is a good way to visualize unsaturated, saturated, and supersaturated solutions. So before you open up your bottle, so this is the before picture. So it's capped. We have excess carbon dioxide escaping with bubbles and gas. Okay, so this is the before picture. So all of my carbon dioxide is in the bottle. Nothing has been opened, nothing can leave. So this is super saturated. Now, as soon as we open up that bottle, you can hear the gas actually leaving when you unscrew that cap. And so that is the excess carbon dioxide that's been put in there. It's leaving the solution. We still have carbon dioxide in there. It's just we're getting rid of all of that leftover carbon dioxide that is not really staying inside the solution because it's oversaturated at the beginning. And then if we leave our solution out, so if we leave this uncapped, then all of that carbon dioxide, the gas particles move really fast. It's eventually going to leave. So that's what will cause your soda to go flat, is when all of the carbon dioxide leaves the bottle. All right, now when we are talking about saturation points, we have what we call solubility curves. So on a solubility curve, we always have the temperature graphed on the x-axis, and we have the solubility on the y-axis. And you're going to have a specific line for every compound. So when we're trying to read this graph, it's really just looking at, all right, in my intersection point, is my intersection point below my line? that's going to indicate that my solution is still unsaturated and I can add more of my solute. If my point is right on that line, so my intersection point is right on the line, anywhere on the line, that tells me that at that particular temperature, that is the maximum amount of solute that can dissolve in 100 grams of water. If it's above the line, that's going to tell me that I now have a supersaturated solution. So anything excess would be either sitting on the bottom of my glass, like we had in the lemonade example, or if it was a gas, it would be escaping the solution, like we talked about in the soda example. All right, ladies and gentlemen, the next video, we are going to be diving into how to read a solubility curve, and we're going to be going through several different examples.